monitoring of the high voltage motors. And to explain acronyms that you can see here, one is HV, which is high voltage, the other one is AC, which is alternating current. So there are many types of the motors, and we'll be focused only on these two types. This seminar is part of the overall maintenance program that is being delivered by Quality Iris Power, and it belongs, or topics that I'm talking about today, they belong to a condition-based or predictive monitoring. And the whole idea with that approach is to learn a little bit more about the asset that you operate without interrupting the production. And information collected during that monitoring is a part of the overall scheme, which includes offline testing and online monitoring. So today's story is about online monitoring, and the differences between online and offline monitoring are easily explained using this slide. If you do online monitoring, machine is running, which is most essential, and it is helpful in collection of the high quality information. In order to do that, it's necessary to install some sensors and provide some sort of connection between the portable or continuous unit used for online monitoring. In an offline scenario, machine will be stopped, partially disassembled, and there is a requirement for a portable test device to be brought to do some sort of test on that machine. There are many differences between offline and online. Each has certain advantages and disadvantages, but generally online is less expensive once sensors are installed, and mostly machine will be in normal operation, which means the voltage, temperature, vibration levels, current level, everything else will be reflective of the normal condition of the machine in operation, unlike in offline test where machine is stopped and some parameters are not present during that kind of test. Since we are talking about electrical motors today, there are many ways how electrical motors can be divided, and this is only one attempt to indicate what kind of motors exist. It's not complete, it's not all-inclusive, but it basically can generate or can separate motors into broad groups: AC, alternating current, and DC, direct current motors. The topic of today's story is, as I said before, is the alternating current, and when we delve deeper in that motors, we can separate them in two models, or two types: synchronous and induction motors. And again, there are many divisions between that two groups, and today we'll be talking about wound rotor synchronous motors, so we are not going to touch magnet rotor. And when it comes to induction motors, we'll be talking about squirrel cage induction motors. So to start, this is a picture of one high voltage AC motor. Well, high voltage, in our opinion, is anything higher than 3.3 kilovolts or 3,300 volts. Most frequently, voltages are in North America 4.16, or in the rest of the world 6.6 or 6.9 kV. And that machines can be large in its size, depending on the number of poles or speed that they operate. So diameter of the motor could be going from 1 or 2 meters up to maybe 10, even more meters. And we are talking about a significant size of the asset, which is powered by high voltage and requires a lot of high currents to be operated. On this photograph, we can see a couple of components of the motors. So we'll be talking about stator first. So stator is covered by this top and bottom shield. And the rotor is visible here. In this case, rotor is Salient pole rotor, and we'll be talking about at the end of the presentation. First, stator winding online partial discharge monitoring. This is similar to monitoring of the generators, and the same basics are used in this approach. Definition is that we are talking about small electrical sparks which will occur in a high voltage insulation or close to that insulation. Reason for that occurrence is the voltage, which is sufficiently high for a breakdown, and the breakdown of two components which are present in a motor, which is solid insulation and air, are widely different. As a result of that, there will be some sparking and arcing on a surface or within the insulation in most of the machine. And process is voltage driven, so if there is a void inside of insulation, that void has a likelihood of having a spark across if voltage is high enough. And it's not necessarily going to happen at every sine wave like we see it here, but it will happen sufficient number of times in a unit of time, so we can be collecting the data, indicating the aging process of the insulation based on a number and the type of the discharges in the stator insulation. Insulation failure process is not going to be very quick, luckily. Reason is that insulations are made from the relatively high quality materials, which is a mica and some sort of epoxy materials. And as a result, it takes years or decades to failure. In some cases, failure could be quick within the months. And the reason for monitoring is to really find out how fast we are approaching that moment. We are not going to predict the moment. We are not going to tell you when machine is going to fail. But based on a measurement that we will provide you, you can get some idea about the state, health state of the machine, and the possibility that the problem or number of problems is going up. Couple of scenarios within insulation can be easily detected using partial discharge monitoring. One of them is delamination of insulation. So insulation is, as I said, combination of the mica and epoxy. Mica is usually applied in a form of tapes. That tapes are held together with either epoxy or polyester or asphalt. And the lamination of the tapes as a result of the change of temperature of the motor and insulation is quite a typical process. So if something like this happens either in operation or as a result of incomplete impregnation of the machine in manufacturing process, this can be detected by partial discharge. Some of the problems are surface, and some machines will have a semiconductor coating. This is applicable for higher voltage motors like 11 kV and 13 kV. And in the case that interface between the semiconductor and a grading coating is not perfectly done, there is a possibility of the discharge on a surface, which can again be detected. And in the case of larger machines with a relatively high current in a stator bars, if a stator wedge is not performing its task, it is possible that bar movement will cause degradation of the surface of the insulation and consequently partial discharge on surface, slot discharge, which again can be detected. In order to do that detection, I mentioned sensors are required. Typically that would be a capacitive sensor, and in a case of a 6.9 kV motor or lower, the smallest sensor on a picture will be used. In a case of the motors which are rated higher than 6.9 kV, the 16 kV sensor will be used. The signals from the sensor will be brought to the termination box, and from termination box, portable or permanently installed instrument will be used. Typically, if motor is cable connected, we will be using only 3 sensors or 1 sensor per phase. And the instrumentation which is dedicated for that kind of measurement is TGAB as a portable instrument, or motor track, which is an instrument for continuous monitoring of the partial discharge with 3 inputs per machine. In a case that motor is larger and may be connected to a system by bus bars, in that case it is possible to install 6 sensors in order to separate system noise from the machine PD, and then it will be installation which is similar to a smaller turbo generator. And again, TGAB as a portable instrument or a bus track as a continuous instrument will be used. This is a picture of one installation. You can see capacitors and orange high voltage cables connecting to terminations, and a black coaxial cable on the bottom leading the signals from capacitors to termination box where some sort of instrument will be connected. So once you have this system in place, the question is, how do I find problem, or how do I recognize how big is my problem? A couple of tricks are used. One is comparing the plots from identical machines, if I have them. The other one is comparing the results to results from an IRIS database, or trending the machine over the period of time. So collecting the data a couple of times a year and looking at the trend or change in a trend of the amplitude of the PD pulses or a number of PD pulses collected. A couple of things can impact the test results, and some of them are listed here. Type of the instrument, type of the sensor, voltage of the machine. If it is not air-cooled machine, then gas, coolant, pressure. What kind of installation, how old is the machine, who made it, and operational parameters. What we also realize is that the system that we use is producing the comparable results from motors and generators. So machine type, meaning is it machine, is it motor or generator, does not influence the result. And also type of the molding resin. I mentioned 3 of them, epoxy, polyester, and asphalt. They do not impact our statistical base distribution. Thanks to the rules we established 25 years ago when it comes to data collection, we were able to produce statistical distribution of the results. So today, IRIS has more than 400,000 test results from different machines. There are more than 10,000 machines in our database. And every year we refresh that results, producing the information to a user, what kind of partial discharge of amplitude can be expected in different types of the machine. We also give some recommendations based on that vast database, indicating that if your machine is in a group of machines with a higher than 90% partial discharge levels, it is likely that it is a very deteriorated condition, so additional attention or additional testing is recommended. This is a sample from our most recent database for the TGA instrument. So this will cover motors and a smaller turbo generators equipped with 6 epoxy microcapacitors. What you see on the top is a rated voltage going in a group. So first column is from 2 to 5 kV, and then going to the right for the higher voltages. And going vertically, you can see distribution of the results. What does it mean? So if you take a look at the first space underneath 2.5, 2 to 5 kV, you can see that 25% of the machines will have a QM less than 8 millivolts. So that is very low partial discharge. But if you go up to 90, then we'll find out that 90% of the machines will have a lower PD than 243 millivolts, which is considered to be high. If you have machine and if you make a test, after the very first test, you can compare your results with the results in this table, identifying the voltage of your machine and then looking at the QM from your result. So you can see, is your machine in a group with a lower or higher or maybe higher than 95, which would be critical group when it comes to level of partial discharge. The summary, it is well-established online method. It is focused for AC rotating machines rated higher than 4,000 volts. And there will be different sensor instruments available, depending on the type of the machine and depend on the approach, is it continuous or portable monitoring. So this would be end of the PD story. I don't see any questions popping up in a few words, but if you have something, we can address that after the end of the presentation. Next story is going to be on a rotor monitoring, and there will be 2 parts because there are 2 types of the rotors. And consequently, 2 types of the monitors are required. So induction motor is the most frequently used motor by percentage, and it will have a, if it has squirrel cage rotor design, then the instrument that we can use there is MDSP3, which is basically current signature analysis tool. Or if you're talking about synchronous motors, which is a little bit less frequent comparing to induction motor, then it will be flux monitoring, which is similar to flux monitoring we do on a hydro machines or on a turbo generators. So we'll start first with the MDSP3, which is covering the squirrel cage motor. You have here a cross-section of that motor. So the focus at this time is a rotor. So that rotor is in the center of the picture, and it is based on a laminated rotor core. What does it mean? That means that the rotor is made in similar manner like a stator. There will be a number of laminated sheets held together, and there will be conductors inside of that sheet, which will be basically some sort of bars, most frequently aluminum bar, and that bars will be connected on each end of the rotor, forming so-called squirrel cage rotor design. So this is one of the pictures of the problems, and you can see the rotor core on the left side of the picture, which is again laminated, and there are some indication that laminations are not kept together. So then you can see the rotor bars coming out, and there are connection from a bar to a ring, and the most likely scenario or most likely place for the problem is a brazing or a place where that bar is connected to a ring. So that is a typical failure, and it can happen in many types of the motors, but mostly it affects larger motors because of the forces associated with operation of that rotor. So this is another picture indicating the shorting ring. So that's the ring that collects all bars in a motor, and there are also possibilities that the integrity of the ring is not going to be maintained in a lifetime of the motor, and each of these problems will affect operational of the motor, probably causing the vibration, which could result in an abnormal Airgap eccentricity. This is also something that could happen as a result of the bearing problems or alignment problems. foundation moving, and so on. So in any case, the ultimate problem is contact between the rotor and stator, which is not desirable situation. And if it happens, then there might be a rotor rub, and if not caught on time, this will lead to the catastrophic failure of the motor in most of the cases. So that's another thing that can be detected using the MDSP3. And there are a couple of features of that tool. It will detect both broken bars and Airgap eccentricity. An idea is to capture the problem as early as possible, so to minimize the expense of the repair, and of course to minimize the outages related to a repair or to shutdown of the machine. So that's the kit. Kit comes in a small hand-carrying device, hand-carrying box. Box contains instrument and a couple of accessories which are used in our data collection. Accessories are different types of the current transformers, which are clip-on, and that's the installation. So there is no requirement for a continuous or the permanent dedicated sensor. Sensor is portable, and the instrument is also portable. And we also provide a tool which is used to measure the speed of the motor, so that can be specified in a software in order to find the flip of the motor in operation. Testing can be done on 2 points. One point is on motor itself, and the other one is on a control panel. So this is MCC, Motor Control Center, where protection for the motor will be installed, and a current coming from the CT connected to a motor is measured. So with a blue clip-on transformer, which you can see on the right side, we can collect the signal, and that signal is then brought to an analyzer, and from analyzer to instrument to the computer, and the results will be collected there. So to summarize, MDSP3, due to its high signal-to-noise ratio, data collected are very reliable, and because of that, we can provide information on a condition of the motor, indicating if it is known how many bars are installed in a motor, we can indicate how many bars are broken. If the user does not know that information, then it can give them an estimate of the factor, indicating a number of bars that might be affected. Measurement can be taken in 2 types. One is quick, and the other one is a higher resolution measurement, which takes a little bit more. Both measurements produce similar results in most of the cases, and the instrument is simple to use. It actually doesn't require your power supply. It's powered by USB port on a computer, and the minimal training is required for data collection and data understanding. That was a story about squirrel cage motors. Now we are going to a different type of the rotor. This is a slide indicating the rotor of a Salient pole machine, which could be used on a hydraulic generator or on a motor. In this case, there are 12 poles on this rotor, and that's indication how that rotor poles are mounted. And as a result of that, there will be different approach in monitoring this kind of rotor. So we are not going to be collecting the current from a motor lead, looking for a current signature analysis. In this case, we are looking for the voltage, which is induced in a flux probe, which will be installed somewhere on a stator. So this is a similar approach like on turbo or hydro generators, where we are looking for an Airgap flux, and that Airgap flux is going to be critical information in maintenance or evaluation of the condition of the rotor. System is based on a sensor, which is installed on a stator core. That sensor can be installed in most of the cases without a major disassembly of the machine, which means that only one cover needs to be removed, and sensor can be installed between the 2 poles. Sensor is inductor. It's a coil that will be collecting the magnetic field emanating from the rotor poles, and based on a voltage coming out from that coil, we'll be able to collect information and display information about condition of the rotor poles. Instrument can be portable or continuous, and that instrument can come in 2 flavors when it comes to a continuous instrument. It could be flux track, which is a single technology instrument, or a guard, where we have up to 3 different technologies. So if your motor is large enough to be significant candidate for a PD monitoring, then with one instrument, which is a guard, you can have a PD monitoring, you can have flux monitoring, and maybe you can have shaft voltage and current monitoring on that motor. So system is based on a installation of the flux probe. Flux probe will be indicating the number of shorted turns per pole. And in that case, we can use algorithms to analyze the results. So there will be 3 of them. Purpose of the 3 algorithms, which are used simultaneously, is to eliminate uncertainties related to Airgap information, which might be different. And in order to distinguish between the shorted pole and the pole which is further from the coil, in other words, pole that produce lower voltage, but not because of the electrical problem, use of 3 algorithms is very effective. So this is a layout of the system. It starts with a sensor on the left side. It is potentially possible to connect this system to a sensor for the speed, so synchronization sensor, so we can see the speed of the motor. Both signals are going to a termination box. From termination box, it will go either to a portable or continuous flux monitor, and then a laptop can be used there to analyze it. So this is a picture which is an indication of the Salient pole shorted turn. There is a burnt spot between the 2 turns. There is a lack of insulation, so this is a turn-to-turn problem. And in the cases of more of shorter turns, it is possible to experience vibration, and vibration again could be coming from mechanical or electrical causes, and this tool is helpful in analyzing the root cause of the problem. So that is, I believe, in shorter turns, just zoomed in. And the final result of the test would be something like this. There will be a graph. That graph will be indicating a number of poles in a machine, and based on algorithm used, it will indicate that if one or more of the poles are in a shorted condition, they will be having a lower output comparing to the other poles, and if that lower output is lower than threshold, which in this case is specified, I believe, as 98% on a red line, in that case the pole will be identified and user will have information in front of him which pole or how many poles are in shorted condition. I mentioned use of 2 algorithms, and it is very important. The reason for that 2 algorithms is to compare one pole result to average value of the all poles on the left side, and on the right side to compare results from one pole to its neighbors on the right and left side. So we are looking at the same set of results collected at the different operating parameters. And on the left side, we can see that the shape of the result is not circular. On the right side, we can see circular distribution of the results. So what's going on? Once you take one pole and compare the reading from that pole to average reading of all poles, result will indicate the geometry of the rotor. So what's visible on the left side is that rotor geometry is far from circular because we have a different proximity of each pole to our flux probe installed on a stator core. Or on the right side, looking at the same result, but just using different algorithm, we can see that there is no group of 3 poles with the different readings. So every 3 poles that we compared produce a similar output. So that's indication that there is no a single pole with a shorted number of turns, indicating lower flux output comparing to the poles on the left and right. So that's the advantage of this multiple algorithms, because it does eliminate the requirement for the Airgap information, which otherwise would be required in order to analyze results in absence of 2 algorithms comparing results to average and to adjacent. To summarize, it is a simple to perform online test. So machine, of course, needs to be operating, same like with PD, same like with current signature monitoring. Instruments can be portable or continuous, and this technology has been used for the last 40 years, and it is very beneficial in vibration analysis, which could be a significant problem in operation of any rotating machine. So that was presentation. To conclude, there are different types of the monitors, and the benefits of condition-based monitoring include extended life and maximized operational revenue from the asset, minimizing the potential for catastrophic failure and shutdown-related problems, which are frequent. Even if you do repair during the shutdown, there is no guarantee that everything will be there as good as before the shutdown, so people try to avoid shutdown unnecessary, and these kind of online tools are helping them prolong the time between the shutdowns in order to minimize the number of shutdowns or investments required to maintain them. So that's the end of the story for today. If you have any questions, I'll be trying to answer them, so go ahead.
So far, no questions, Mladen.
Okay, we can give them a couple of minutes to see if we're going to get any, or maybe everything was so clear.
If anyone has any questions, please feel free to type them in the bottom right-hand corner of your dashboard in the chat functionality, and we'll be happy to address anything. Just to recap as well, I will be sending the recording and the slides after the presentation is over. It may take a couple of hours or so, but you should get that sometime today. Okay, we do have a question. Okay, what is the minimum air gap for the flux probe? Malden, did you hear me? Laden?
Yeah, I heard you. What's the minimum? I didn't. It looks like you didn't finish the question. What's the minimum air gap for what?
What is the minimum air gap for the flux probe?
Okay. So flux probe is about 3 millimeters in height, which is 1/8 of inch. And if air gap is bigger than 3 or 4 millimeters, it can be installed. So typically, we did not have any situation where machine design prevented us from installation of the probe. So
okay.
We need about 1/8 there, let's say, or 3 to 4 millimeters.
Okay, great. What determines the eccentricity of the pull flux diagram?
There are two stories about eccentricity. One is based on a Salient pole machine, which is this one. So here we really don't express eccentricity in any kind of number, which is only visible as a result of the indication or whatever graph you have on the screen. However, when we are talking about squirrel cage motors, in that case, eccentricity is measured, and it is measured based on harmonics in a signal that we analyze. So this is basically current signature analysis. I didn't go very deep in explaining the results, but eccentricity will be expressed in a number, indicating that as a percentage.
Okay. Offline rotor bar testing with, let's see, it says offline rotor bar testing with an LCID tester.
That's true. This kind of problem can be detected by offline testing. So in a case that your failed connection or a broken bar is not visible, or it's not outside of the core like here, which is again most frequent scenario, then LCID or MCT, which is a LCID younger brother, which is unfortunately not anymore in a sales program, motor core tester, can be used to detect the location of the bar that is broken. So that is a simple test. What is recommended is to put a couple of amps of a current through a rotor cage, and then scan the rotor surface with a Tracll sensor circumferentially going around and looking at the response. So identifying the basically current flow underneath the rotor surface within the laminated rotor core using the Tracll as a sensor. So that can produce the result indicating where is the location of the bar that does not conduct the current. However, this will result in a positive identification only on a bar which is broken rather than bar which is cracked. So if there is a still electrical conductivity within the bar, in that case, this wouldn't be a tool that will help you understand or locate the problem.
Okay. What type of connectors are used from the PD couplers? Is it BNC style?
Yeah, it is BNC. So
okay.
I don't think, actually it is visible on the bottom of this graph, well, not so well visible, but there are 6 here and there are 2 on the side. So it is a BNC connector.
Okay. Let's see. Is it possible to install Flux Probe online?
Online, we don't like it. It's possible, but the only way how you can do that would be really to go through the stator core from the back of the machine while in operation and put some sort of sensor which will be going through the air vents and don't go too far to hit the rotor which is spinning. So Iris, because of that reason, do not produce the type of the probe that can be installed that way. However, some other people experimented with similar approach. So if you make a coil and you push that coil through the air vent from outside of the core diameter, it is possible. So answer is yeah, possible, but not highly recommended because of the fact that you might not be very precise in positioning of the probe, so that probe could hit the rotor.
Okay. Is mapping of the original install of the Flux probe necessary to determine later condition of the monitor?
Can you repeat the first sentence?
Sure. Is mapping of the original install of the Flux probe necessary to determine later condition of the motor?
Mapping? Is mapping of the... I don't get the question.
Well, I have the question asker, and we can email him offline after the webinar.
Okay. So
we have another question. What is used for the key phaser indicator? Is this a separate probe? What is the application of the key phaser in the rotor and pole analysis?
You are coming intermittently, so I guess question is about sensor for the rotation, which is on the bottom here. That's separate sensor from the flux probe sensor, but signals are brought to the same instrument, if that was the question.
Yeah.
You're coming off, I don't get the complete question.
Okay. Let's see. I think that is it right now. Are there any other questions that have come in? Oh, we have one. It's a comment to the last question. A flux probe could only be installed online if the stator is not hydrogen cooled.
That is true, but we are talking about motors today, and most of the motors are air cooled.
Okay.
But the comment is accurate if you are talking about generators.
Okay. When the flux probe is installed, one would run a test and map the as-new performance of the flux. This creates a map of the as-new installation. We would like to look at changes to see age-related alterations.
Yeah, that's possible. Now I understand what's mapping, or maybe that was related to a question that I didn't understand. Correct. Similar like other technologies, trending is an important tool. And software will enable users to trend each pole over the time. So there are different graphs indicating how trending is being done, and we can provide that as a typical trending diagram, which we use in many other softwares. So yes, trending is also used in a flux monitoring, comparing the baseline readings on a new installation and looking at that machine over the number of years.
Okay. Is the termination box okay for hazardous location, or is there one available?
For PD, or for flux, or for, depend on the rating. Depend on the rating of the hazardous location. We do have hazardous location certificates for the flux probe. We have it. So flux probe itself can be installed in a hazardous rated motor. A signal that comes from a flux probe is relatively low frequency, so it can be led with a longer, up to 150 meters long wires. So there is no reason for a box to be within EX1 zone at least. So the approach in installation of the flux monitoring on an explosion rated motor is to put the probe inside and to bring the box to the place where there is no rating anymore. So answer is yeah, that way. On a PD, the similar approach, the sensor's installation of the sensor needs to be done in a manufacturing process, so not to affect the rating of the motor. So in that case, it is possible to do the same approach to monitor the explosion-proof rated motors for the PD and for the flux.
Okay. Can you identify surface insulation gap from deep insulation in PD? If so, how?
Insulation gap. Well, I presume the question is based on a gap either within the insulation or maybe on a surface of insulation, like in this case here.
Yeah.
No.
Yes, they're saying surface insulation.
Okay.
Surface insulation.
So if you're talking about stator winding, then we are not measuring that gap, but the gap will be affecting the amplitude of the pulse. So in the other terms, if gap is bigger, we are going to have a longer, higher amplitude pulse. So when we analyze PD results, we look at both number of pulses per second and the amplitude of the pulse. So number of pulses per second is indicator of how many voids you have or how many gaps you have. And the amplitude of the pulses is indication of how big that gap is. However, there is no clear correlation saying that a 500 millivolt pulse corresponds to a 1 millimeter or whatever 40 tau of the gap. So there is no such rule.
Okay. Is this technology, PD and Flux Monitor, applicable to lower voltage motors by using different sensors?
Well, when I said on the beginning what is AC and what's HV, for us HV is higher than 3.3 kV. So if it is lower than 3,300 volts, potential for the both problems is very remote. So answer is it's not recommended to install it. There is nothing to prevent you from really installing it, but benefits of such installation would not be really easy to explain or calculate, because you will be installing the sensors on a motor where likelihood of PD is remote because of the very low voltage. So technical answer would be really no, there is no significant benefits of monitoring PD on a, let's say, 690 volts motor or any motor which is like 1,000 volts.
Okay. All right. What sidebands does the MDSP3 look for?
Many. It will be looking at one type of the sidebands for the analysis of the broken bars, and then it will be looking for other type of the sidebands for analysis of the Airgap eccentricity. So additional slides could be provided to explain this question if you get an email from the user who is asking this.
Okay. All right. Any other questions? Okay, just to reiterate to everybody that I will be sending out the presentation and the recording of the webinar later this afternoon. When you get that email, if there's any questions that you have that have popped up from now until then, feel free to just reply to the email and we can answer your questions as well later on. We'll hang out for another minute or two and see if anything else pops up, but otherwise I hope everyone has a wonderful day or a wonderful end to their day. Thank you.